Welcome to this session on the Advanced Large Language Models course. Today I'm going to talk about text generation with multimodal inputs, right? So in the previous session we talked about multimodal encoder models. In this session I'm going to talk about text generation with multimodal inputs. Let's start with a few basically applications where this text generation with multimodal inputs matters. And in fact, I have a bunch of those applications just to sort of motivate the kind of use cases people are applying these technologies for. So for example, this one is visual conversation. So this has become so popular now. I mean, you have like so many chatbots all around. So you have Microsoft Copilot and Gemini and ChatGPT, etc., where you can basically upload an image, also put up a question, and then the model generates an answer. And the interesting part is that it also retains context. So essentially there is a memory buffer which basically also manages context of the previous turns in the current conversation. In fact, some of these systems also retain a user context across conversations by doing user modeling and then retaining some sort of a user profile, right? And these conversations could be pretty long. So in the sense that you could actually, ask very, very creative things like creating a blog post around a particular scenario and so on, right? So very, very rich conversations, multilingual conversations and so on. Scene understanding is yet another sort of multimodal task where you could basically upload an image and ask, what could have happened based on the current scene. So this is not just descriptive in nature, but also does a whole bunch of reasoning, understanding world knowledge, sometimes also understanding common sense that, what could have happened that could have led to this kind of a situation and so on. Right? This is about actual knowledge-based sort of base generation. So maybe what you want to do while generating is not just depend on the pre-trained knowledge of the model, but also combine it with the knowledge that exists in the knowledge base. And essentially then generate stuff. So knowledge grounded image descriptions, for example. Right? Visual question answering just by itself is also an interesting task where rather than doing full multi-turn conversations, you just want to sort of generate an answer, direct answer based on a question for an image. And these examples are super popular, essentially coming from the oldest GPT-4 papers, right? And then almost everyone sort of tries to show the results with the different kinds of models on these examples that you see. I mean, what is abnormal about this image, or can you explain this meme in detail kind of examples, right? So both of these examples essentially, for example, what is unusual about this image? Yes, there are models which can generate very long outputs detailing what is unusual, but then, well, I mean, there are also latest models which basically give you very, very pinpointed, accurate output, saying that the unusual thing is that my man is ironing clothes on a ironing board attached to the roof of a moving taxi, which is not really very usual. Similarly, there are models which can give you very, very crisp answers or detailed answers depending on whatever is the style that you prefer to get those answers in. And all of these models, after all, are processing text and image and then generating text as a response to the input image. So these models don't just do image and text as input, they also can take audio as input. So where, in this system, you could basically take the video, pass on the video, and then you can actually, so this is Video-LLaMA. We'll talk about Video-LLaMA also when we start talking about architectures. But here you essentially just take the video, the user asks, describe what you hear, and well, it can basically describe the dog barking sound. But then it also has visual capabilities, so you can basically, user can ask, does the man wear glasses? And the system does have a visual capacity as well. Right? Similarly, this is another example where the audio processing capabilities can be observed. When the model is asked how was the audience's response, it can actually nicely explain that the audience was very enthusiastic and clapped loudly and so on. Okay. Common sense concept recognition. So essentially, this is basically a pic from a scene in a movie. Do you know who the man on the right is? And it can actually nicely relate celebrities. So in some ways, yes, these models can understand celebrities, relate them with world knowledge or knowledge graphs, basically, so as to be able to figure out who is playing which kind of a role in which movie and so on. Landmark detection as well. So in the sense, yes, it basically recognizes popular buildings and can explain about them as well. So many of these things that we discussed were essentially describing world knowledge or describing static snapshots, but it can also describe videos. So what are the actions which are ongoing, and then also do question answering based on the actions. So either just describe the actions in deep details, but also sort of describe the actions and answer questions based on that. So for example, summarize is okay, but then the question is what direction is the ship going? So it does understand what was the direction in which the ship is moving. And then people have used it for all kinds of creative use cases. So in 2022, when these models were not so accurate, or early 2022, we were ourselves working on a task of comic strip generation. So the idea was that, hey, based on the previous few frames, can you basically try to come up with the text that those cartoon characters would speak in the next frame? Now people basically use these kinds of models for doing all kinds of interesting creative generation, like can you write a story around this image? Can you write a rap song that vibes with this image? Or who are the people in this image? I mean, when you give a comic strip and so on, right? So these are all examples where text is being generated given multimodal inputs. More examples. These images are essentially more of snapshots of web text. So text extraction and detailed reasoning based on image, where this is basically a snapshot of an article, and then and then somebody could say, oh, please identify the text in the picture. You might have heard about the DeepSeek OCR, which came up very recently. So, which is more or less, has super awesome capabilities of doing these kinds of things. It basically understands the text which is embedded in the image itself, right? And then this is a response to this question. Hey, this is the text which is extracted. This is using MiniCPM-LLaMA 3, but yes, DeepSeek OCR is known to do even better. Okay. But there could be other kinds of interpretations based on the text of the image, like based on this picture, make a detailed meal plan for me. Yes, there is a detailed, nice meal plan which it generates. Based on what is a healthy diet, and obviously all of us studied this in school, balanced diet and so on. Okay. These systems now can also process very long text in different kinds of, or very long, so images which are basically depicting, articles or paper cuttings in different aspect formats, right? So for example, this one is a tall format. This is basically a continuation of the entire paper cutting in that senses, and you want to capture that story. Yes, different aspect ratios also are reasonably okay with today's models in that senses, right? Flowchart understanding is yet another kind of image image to text kind of problem. So you have a flowchart of this kind. How does it work? Right. So essentially, understanding natural images is one thing, and being able to generate descriptions of those. But the other thing is basically taking structured images like flowcharts or patents. We also worked on patent diagrams. So those kinds of infographics, and being able to nicely come up with text that describes those, right? Text that describes those. This is the right one is for interior understanding. So these are different domain specific things. Now there is obviously also work on medical understanding. So given medical images, try to write diagnosis, possibly also link with ICD-10 codes, which are like standardized medical codes for that diagnosis and so on, right? So people have done generation in a domain specific manner, where basically the images are not really the usual cat and dog images, but more of flowchart images, infographics, bar charts, and plots, and patent diagrams, architecture diagrams, things of that kind. Very recently, we have also been working on the other way around problem. So obviously you can take architecture diagrams and generate text, but orthogonally, which we'll not discuss in this session, is also the task of image generation or video generation and things of that kind, where given, let's say, text describing how a system works, can you generate architecture diagram automatically, right? But that's orthogonal. So this session is more on text generation. It's multimodal session, but it's a session on multimodal inputs, but output is text. More examples, understanding menu cards and infographics. So we already talked about infographics. Yes, take this kind of a chart and explain this stuff. People have been using these kinds of things even for writing papers these days. I mean, essentially, almost everyone, when we write papers, essentially take an infographic and obviously manually describe what is going on in that. But more often than not, you also ask GPT, hey, can you basically describe it in a better manner to me? Yes, if there are interesting insights that a human could not really look at, you could basically have these models generate those insights, and you could then include them in your write-up, right? So those are all, last one, basically BLIP parsing. So essentially, we did discuss this in the previous session as well about document layout parsing and so on. But here is a very interesting, this is an interesting example in the sense that it just does not parse things, but also engages in a conversation based on the parsed data. So here is a receipt from some store, from some restaurant. And then this guy basically says, I only had the sliced meat. How much do I need to pay? Include a 18% tip. Now, the kind of capabilities that the model needs to have to be able to answer this question is very, very interesting. So it needs to be able to not just parse this stuff and do OCR, but be also able to relate that, hey, what would sliced meat mean? I mean, there are like, sure, I mean, there are like 4 or 5 things which are ordered here. And there are those entries, four entries basically that I see here, which one basically relates to sliced meat. Okay, and it also requires then language translation, so or understanding, which could have, I mean, maybe this does not directly translate to meat, but having that understanding that this is the one that relates, this is the entry that relates, and then being able to take that amount and add 18% tip as expected, and then finally putting up the amount really involves a whole bunch of capabilities, right? Not just visual understanding, but being able to translate, being able to relate what contains what, being able to take the align the the amount 36.5, being able to do mathematical reasoning on top, adding the tip and coming up with the final answer. Yeah. So all of those are interesting capabilities. So what I did in the first part was to basically talk about various kinds of use cases where multimodal input but text output makes a lot of sense, right? So several use cases. Okay, yeah, I mean, at the base, it's basically just perception parsing, perception understanding. So in the sense that understanding the image, but beyond that, there's a whole bunch of effort that these architectures need to make in terms of combining reasoning on top of the perception that has been already performed, right? So now what I will do is to basically start talking about various models, and starting from the historical perspective to some of the latest ones. We may or may not have time to talk about all of them, especially in detail. I mean, I try to go into a significant amount of detail that you can understand the main idea, but clearly, I mean, if you want to understand more details, you should look up at the paper, right? So the first thing that you could do to be able to generate text is basically obviously take image as input, pass it through a vision encoder, like the ones that we learned in the previous session, right? Take the text and pass it to a language model, language encoder. Take those encodings and essentially pass it to a autoregressive language generator, right? So that's that, and that's what the frozen model does. I mean, the name itself is so explicit that, hey, I'm going to freeze my embedding model. I'm going to freeze my or maybe the vision model, maybe I'll freeze or I'll basically learn, but I'm surely going to freeze my text part completely, and all I'm going to do is to also take the input image, project it to the dimensions. In fact, at that time there was no projection logic, sorry. So I'll basically therefore just take the vision encoder. I will unfreeze the vision encoder. So basically I'm going to train my vision encoder, but he is going to generate the output one token at a time, right? And you train it in a end-to-end manner such that you keep the language model parameters frozen, but you update you see the vision encoder parameters as you fine-tune it on this image captioning data. So you fine-tune on image captioning data, you give the image, and given the first 4 words, you're going to predict the 5th word, 6th word, 7th word, one by one, as you typically fine-tune any generative model. It's just that you have an extra input, which is basically the image embedding, right? or image encoder. So basically you do fine tune the weights of the image encoder. Right. Now at inference time, you could use it in various ways. You could basically just do zero shot VQA. So in the sense that you pass on the image, you pass on the question, and obviously the weights are all fixed and so on. So after the question has ended, it basically leaves you with the prompt, and the next token essentially tries to predict the answer. Next token tries to predict the answer. You could also do one-shot VQA, which basically means you can give the image and you can essentially give the question and the answer together. That's a one-shot example. But then you can also give the image and essentially in the question without the answer, and hopefully it generates the right answer. Or you could do few shot. So essentially you could give the image and then some sort of a caption, another image, some sort of a caption, and the third image, and then ask what should be the caption or what should be the classification for the third image. Right? So this is basically obviously test time changes that you are doing, inference time changes via in context learning. The first thing that people could do in history from a historical perspective. Right? In hindsight, if you think about it, hey, why do you want to basically update the entire weights in the vision encoder? Could you basically just keep the vision encoder also frozen and probably just learn some sort of a projector embeddings which project these vision model to the same text space and make it work and so on, right? But in the beginning, that's what people thought. They basically called it the frozen model, where, well, the language model is frozen, but the vision model is trained, and then at test time, you could basically use it in the zero shot, one shot, few shot settings, right? So and this model basically was not trained on multi-image data. So in the input, there is basically only one image, and the output basically just has one caption associated. So the pre-training data is basically of that kind. Right. By the way, there are now models which basically have been trained using multiple images in a conversation style. Also, there have been models which have been trained such that all the images are upfront provided, and then the conversation works based on that. But there are also models which basically have interleaved image and text kind of scenarios. So you basically have some text, and then you have an image, then you have more text, then you have another image and more text and so on. That's interleaved image and text scenarios. So for certain kinds of scenarios, you do need that interleaving thing. So when you are trying to think about a scenario where you want to apply such a model, you want to also think whether the model was trained in an interleaved setting or not. Right? So that takes us to the next model that I'm going to discuss. This is called Flamingo. So in this model, you can actually have multiple images in the input. So that's that. If the input is this, there's an image, and then there is a very cute dog is the caption, and then there is a cat, and then this is. So you want to obviously predict a very serious cat in that sense. Okay. The way this works is the architecture that you see here. So let me basically talk about the architecture. In this architecture, there is vision processing which is happening on the left side, and then there is text processing which is happening here. Okay. So images basically are represented. I mean, when there's text processing which is happening in the text tower here, essentially you see the text processing. In the text part, you basically place these sentinel tokens or representative tokens to basically mention that there was an image here. You don't really specify specifically contain the image tokens there, but you basically just mention that there's an image here. Okay. And this one is the standard, is more or less the standard transformer decoder. So there's not too much of a difference. As you can see, there is some sort of an attention and there's feed forward and so on, but there's a slight variation. So in the sense that although there is feed forward and self-attention, I mean, this block is slightly different from a standard transformer decoder, but more or less it does the same job. Okay. In fact, this block actually contains two sub-blocks, and if you really look at it, this one is you see, I mean, essentially it has gated cross attention dense, and then it also has a LM block. So LM block is basically the standard transformer decoder that you have learned about. It has self attention and feed forward internally, but then there is a gated cross attention dense, and this gated cross attention dense is slightly different. Okay, it is slightly different in the sense that, well, self attention is actually replaced by cross attention, and you have a feed forward layer as usual. Okay. However, around them there is gating also, and that is why it's called gated self-attention. Gated networks are again gated. This gating thing is actually a popular primitive that is used across many architectures. It just means a dense layer which sort of predicts how much importance do you give to each of the attention heads or each of the inputs and so on. Okay. Now, why cross-attention here? I mean, cross-attention makes sense here because, hey, it's not just that you want to process the text. You obviously want to also have the influence of the image. So it's to basically when you're generating stuff. Now, how do you bring the influence of the image when you're generating stuff? Well, the influence of the image flows in through these cross-attention connections. Okay. So our decoder guy, our text decoder guy, this guy essentially is sort of generating the text output, but that needs to be conditional on the images that are also there as part of input, right? And this conditional behavior is basically brought in using this cross-attention logic. And I'm assuming you sort of understand cross-attention. Yesterday also we talked about it, where in Wilbert basically there were those cross-attention kind of things. You're taking keys and values from the other modality and queries from the text modality itself. So the queries are from the language modality itself. The keys and the values come from the vision modality. Okay. So, I mean, Flamingo has basically 3 different variants: 3 billion, 9 billion, 80 billion variants. And for encoding images, basically they did not use the transform models yet. They use the ResNet models. So they still come up with some sort of embeddings based on ResNet, and they essentially pass them on as extra input, which flows in via cross-attention connections to the transformer decoder for generating the text. Okay. Yeah, there are some details about the data sets that they used for training, but more important stuff is to really focus on the vision tower now. Okay. So on the vision tower, if you observe, there is a vision encoder, which was basically based on pre-trained ResNet model and kept frozen. Okay. But then there is also this thing called as perceiver resampler. Okay. There's also a perceiver resampler guy. Okay. Now, what does this perceiver resampler guy do? Okay. It's I tried to talk about it yesterday as well in the afternoon talk. But the idea is that perceiver resampler essentially is typically used when your input is can be variable sized. For example, in this case, there could be multiple images, and then what do you do? Right, and then what you want to do is to really extract the essence of all of that input and convert it to a fixed size representation, a fixed number of vectors, okay, fixed number of embeddings in that senses. Okay, so let's talk about what is this perceiver resampler guy. I mean, hopefully the remaining part of the architecture is super clear, but this perceiver resampler, what is this guy doing is what I'm going to talk about on the next slide. Okay. Now, not to sort of overwhelm people, basically the left part is just the architecture from the previous slide. That's not a new thing. The new thing is on the right side, which is the perceiver resampler architecture. Okay. What does this guy really do, right? So essentially, and what does it contain? Okay. So I'm really talking about this box. Okay. So what does this guy do? Okay. So perceiver resampler essentially is just a transformer encoder model. So it's basically, maybe you can think about it as a 6-layer transformer encoder model. Okay, so that's basically that guy, 6-layer transformer encoder, right? So what changes is basically the input that you provide to this guy broadly. Okay, so the input, if you have these 2 images, so you take the images and you tile them like you would do that using vision transformers, or you basically get the representations from a ResNet model. Whatever is the representations, you have some tokens in some ways, right? Whether you get them from ResNet or you basically get them from vision transformer as tiles, right? So you have those tokens, and you essentially flatten those things. I mean, if you're getting from ResNet, well, you have to flatten them because they're volumes effectively, so you have to flatten them. Okay, and you pass those image tokens. And remember, this could be variable sized because if you have 2 images, you'll have 2 tokens. If you have like 5 images, you have like 5 into x tokens, whatever is x token number of tokens per image. Okay, but what I wanted to do is basically have a fixed number of vectors to represent this variable sized input. And the way this guy does is by basically to this transformer encoder backbone, the inputs that are passed are not just these variable size things, but also these latent learnable queries. Okay, so if I really wanted to represent whatever is the number of images, represent them using just 32 vectors. Let's say if I decide 32 vectors, then I would pass in 32 learnable queries. Okay, and when you have these 32 learnable queries, the idea is that these learnable queries act as actual queries in the self-attention kind of a thing, and these other guys basically, so essentially, if you think about the query part, well, it's going to be these learnable guys, and the keys and the values are supplied by both the blue and the purple part, which basically means that these keys and values are these guys and these guys together. Okay. So what you're trying to do is to really come up with transform representations for those queries by borrowing influence from the variable image input. Okay, borrowing influence from the variable image input. Okay, so what you're trying to do is to basically take these images, these vectors, they act as keys and values, but your main goal is to really take these query vectors and transform them nicely, because that's going to be your output. Okay, you're not going to output your variable part that came in, but you want to capture all the influence, all the semantics in it, and include them in your fixed sized vectors. Okay, so these are learnable vectors. You know, I mean, this thing really reminds me of a very old thing that existed even before transformers came in. Even before transformers came in, people used to do this self-attention, so to say. But the meaning of self-attention at that time was very different. To be able to represent a paragraph or a document, you know, you would have a vector which is learnable across multiple things, and then that's the same thing that they're doing here. I mean, rather than having one vector which is learnable, they have multiple vectors which are learnable, and you call them as queries. You know, that's now going to be a representation of your variable sized input in that sense. Okay, so perceiver resampler is now a component that is actually used across many models, many places, wherever you want to sort of take your variable sized multimodal input and convert it to a fixed number of vectors. Now let me fast forward and talk about BLIP. So BLIP series of models. BLIP stands for bootstrapping language image pre-training. I mean, I think they borrowed the terminology from CLIP, but it does other kinds of things. I mean, well, bootstrapping was probably not a great acronym or a great part to put in the system, but anyway, we'll talk about the system. So while CLIP is basically for understanding, BLIP is for generation and understanding. In fact, the claim was that, hey, we just don't do image understanding or multimodal understanding, but we are going to also generate based on that understanding. Okay. Their model architecture is pretty elaborate, as you can see, but it's pretty simple to understand in some ways. Okay. They also use image captioning data to pre-train their model. As you can see, there are these 4 towers in their model, literally, right? So the input could be this, the image, and the caption is this: a little girl holding a kitten next to a blue fence. That's the caption. Okay, and you want to pre-train the model based on these kinds of data samples, right? So you take the image, and the first tower is basically an image tower. You essentially, that's literally like a VIT tower. So in the sense that you take the image, tile it out, and each tile is basically a token. You project the token, give it to multiple transformer encoder layers, which in turn contain self-attention and feed forward. Okay. So that's basically your image encoder tower in that sense. There's a text encoder tower. You basically take the entire text and you essentially you prepend that CLS token to the text, and you give it to your traditional BERT style transformer encoder. So there's nothing specific about this tower as well. I mean, as you see, this cross attention guy is not there. I mean, it's not there. It's basically just self attention and feed forward. Okay. So literally, if you really just focus on this part of the model, it's just CLIP actually. Right, so essentially there's a VIT style image encoder, there's a text encoder as well, and then to pre-train, they actually also have the same kind of loss function, ITC, image text contrastive loss. So image text contrastive loss. So literally this part, the half part, the left half part of this model architecture is CLIP. Okay, is CLIP. Okay. But then there is a right half part which is doing some more fancy stuff. So basically, therefore, let's talk about the right half part. So in the right half part, they basically want to do yet another thing. This tower is still not generating things. So the generation is actually happening only in the last tower. Okay. So this third tower, let me call it third tower, is still an encoder. It's still not a generator. Okay, it's an encoder which tries to come up with an image and text combined representation. Okay, so in the sense that it basically takes this image representation from here and the text representation as input, right from there, and it has a self-attention, bidirectional self-attention anyway, but it also has a cross-attention, and via cross-attention it's trying to take the image influence and come up with a image influenced text representation in some ways, right? It's an image influenced text query in that sense. Okay, and on top of that, it's basically applying this ITM, image text matching loss. Okay, so in that sense, is if you think about CLIP basically just suddenly ignored the visual BERT and Wilbert's image text matching loss completely. Okay, and what this guy has done is to basically not just to preserve the CLIP's image text contrastive loss kind of thing, but also image text matching loss. Okay, specifically as a third tower. Okay. That's that. And then, but this is all for understanding. This is all for coming up with better and better representations for image and text. But how about generation? Okay. So now once this, and by the way, right, since basically you have a loss function here, it obviously influences your image encoding. So obviously these weights are much better and you can come up with a much better image representation. Okay. So therefore, the generation which is happening here basically makes use of a much more improved image representation. Okay, you come up with a prompt. So essentially, you say decode, and you want to decode it, token by token. So you basically just give decode as a token. There's a causal self-attention, which is what you expect anyway on a transformer decoder. But there's cross-attention as well. So basically, this tower, the fourth tower that you see, is practically the decoder tower of a standard transformer model, right? It's just that the kind of input that it takes is much better image embedding, which is influenced by the text as well, because it ensured that image text matching happens fine. It ensured that image text contrastive loss is good, and therefore the input is basically much more accurate, leading to higher quality language modeling. Okay. Overall, it has three loss functions as we discussed: image text contrastive loss, image text matching loss, and then language modeling loss. Okay. The next version of BLIP is BLIP 2. And in BLIP 2, they actually changed the architecture significantly. So this is, literally, I don't know why they still call it BLIP 2, maybe to really represent the same group. But it changed the architecture significantly. And the architecture is more closer to what you observe in today's world when you think about multimodal architectures, which basically, take image and text as inputs. Okay, they don't really have these 4-tower kind of models. Again, from an efficiency perspective, this is actually heavily inefficient because doing a forward pass through 4 transformer towers is going to cost a crazy lot. Okay, so what people do in BLIP 2 is to really it also does it also does text generation, but the way it does is essentially, this is the input, this is the output. Interesting input output, especially for this audience. Yeah. So basically, you see, you can actually take the you can take the image, pass it to an image encoder. And as you can imagine, it's borrowing the concept of the perceiver resampler, in the sense that it's basically taking the perceiver resampler concept, taking variable sized text, right, along with the image, and converting it to taking the fixed size queries. So essentially, this QFormer guy, as they call, is literally a perceiver resampler, similar kind of a method. I will talk about that one on the next slide. It's similar kind of a method which takes learnable queries. These queries are learnable queries, so they are basically vectors that have to be learned. Okay, it takes the so your input contains image and text, obviously. So the image goes to the image encoder, text goes to the text encoder, or rather this querying transformer. Actually, text directly goes to the querying transformer, and then there are these queries. So these queries are actually are the ones that are fed to the large language model. Okay, these queries are the ones that are fed to the large language model. So what do these queries do? Via the QFormer, the queries are trying to express the semantics from the image as passed on by the image encoder, along with the semantics in variable size text, and convert it to fixed size query vectors that are basically passed to the large language model to generate outputs. Okay, that's what basically is going on here. Okay. They pre-train it in 2 stages. First, they basically vision language representation learning stage with where they freeze the image encoder, and then the second one basically with a frozen LLM. Right? But this will make more sense when we sort of look at what's going on in the QFormer. So the QFormer, as I mentioned, in the basic world, you could just think about it as a perceiver resampler, which is trying to take semantics of the image and semantics of the text and trying to compress them into a fixed number of vectors. And then pass it to a large language model. This also made quite some sense in 2023 because large language models at that time had limited limited max sequence length that they could process. So unlike today's models, which can process as much as you want, like millions of tokens as well, thanks to advancements in the way attention is computed and so on, right? Well, let's try to understand what this Q-former guy is. And as I said, broadly it sounds like a Perceived resampler, but it's much more actually. Okay. So this is a expanded diagram where I'm going to talk about this Q-former guy. Okay. So just to sort of again stress, this is the Q-former guy, right? And its job is basically to take image and text and encode it in a way, in a fixed number of vectors kind of a way. Okay. So it's going to therefore take image and text. So it's taking image and it's taking text, and it's basically taking those learnable queries. Learnable queries, representation for these learnable queries as you get them is basically passed on to the next module, which is the LLM guy, the decoder guy. Okay. Now it's doing some fancy stuff here, and therefore let's talk about it. So Q-former actually internally is basically an image transformer and a text transformer. So there is a tower which basically processes images, which is this tower, and there's a tower which processes text. Okay. So, and these towers basically are just transformer encoder layers. That's that. Okay. The idea is that the input is processed using image, the input image is processed using image encoder. It comes up with several tokens. So several tokens representing the image. In fact, the number of tokens could actually depend on the resolution of the image. So if the image is short, small, or large, depending on that, the number of tokens could be different, because BIT models, as we discussed yesterday, they have a fixed size patches. So if your image is large, well, the number of patch tokens are large, right? If the image is small, the number of patch tokens are small, and so on. Okay. So both of them are transformer encoder models, as you see, except that this guy also is a cross attention. The cross attention is the way that it actually takes the image input. Okay, takes the image input. Okay, on the text side, it's a standard text. It's a standard transformer encoder. No surprise there. It's a self attention and feed forward. Okay, but then the way that these two towers interact is what is very, very interesting here in this particular architecture. Okay, and that is why they actually call the entire thing as a Q-former rather than talking about those two blocks separately. Okay, so there is I mean, as you can imagine here, there's self-attention, cross-attention, and feed-forward. So it looks like again a standard, standard transformer encoder, except that it also has cross-attention. I mean, which is not then a standard transformer encoder, but well, it has to somehow include the image influence, and therefore it has this cross-attention. So yeah, one could probably think about it more like a transformer decoder architecture, but not causal attention. The attention is not causal. That's the point, right? So attention is bidirectional in that sense. Okay. Now, how do these two towers talk to each other, and then how are the loss functions defined? So basically, while training this guy, you have like 3 loss functions. Remember, while training this guy, you have 3 loss functions, and these loss functions are different from the language modeling loss that you will have at the end. Okay, so they are different. Okay, so you're basically just training this guy right until here with these 3 loss functions. Okay, so what are the 3 loss functions? Well, image text matching, image text contrastive learning, and image grounded text generation. So basically, these are like standard loss functions that one can imagine. Okay, image text matching and image text contrastive learning we already talked about, and since this is a generative model as well, you are trying to basically also have text generative loss. Okay, now the way that these two towers interact is as follows. For each of these three loss functions, you have a different mask in the way that both of these guys talk. I mean, these two towers talk to each other at every layer. Okay, so for example, in image text matching, you basically have a bidirectional self-attention mask, which basically means that you do early concatenation. Think about it like visual BERT. So in visual BERT, you basically give the input image and the text tokens together, and you let them interact completely, right? It's basically like it's a concatenated input, and now you don't care about which modality that came from. You basically let it interact completely. Okay, so basically this is a mask where if you look at the learnable queries and the text, yeah, this is Q, this is T, all of them interact with each other. There's no masking at all. So there's complete self-attention across the two towers, right? Bidirectional across the two towers. Okay. And this makes a lot of sense, because when you are trying to do image text matching. You let it basically come up with full information transfer across both of them, and then take the benefit of early concats to come up with better embeddings. Okay, but you also have image text contrastive learning, more like CLIP kind of setting. So in CLIP kind of setting is a 2-tower setting. It's not early concat. You basically have a separate vision encoder, text encoder, and then you basically concat only at the end. And which is what is going on here. You do masking. So in the sense that query tokens only attend to other query tokens, text tokens attend only to text tokens. And query tokens, by the way, are representative of the image because they are, after all, taking the image representation via cross attention in that sense. Okay. So that's that, right? And in between, you have this generator guy, right? I mean, in the sense that it has to do image grounded text generation. So therefore, here the way the attention is defined is that it's actually causal self-attention. Sorry, I think I mentioned it's a transformer encoder. It's not. It's a causal self-attention because it has to do generation. So the idea is that so every token here attends to not just the previous tokens in the text, So every token attends to previous tokens in the text, but they also attend to all the tokens on the image, Okay, so that's the masking that is happening here. Okay, so QFormer technically is a very, very elegant architecture. It's a very interesting architecture, the way they sort of transitioned from a CLIP kind, or rather merged the CLIP kind of thinking and the visual BERT kind of thinking. So CLIP kind of thinking is late concat. Okay, or 2-tower models, 2 completely different towers, while visual BERT kind of thinking is early concat, a single tower kind of a model, and then you combine it with decoder, right? So that's a very, very cute and elegant kind of an architecture to think about it. Okay. So that was BLIP 2, and yeah, I mean, after your QFormer training is done, basically this part is the QFormer training that we are talking about. You take the query representations, pass them, do a projection, pass them to a LLM decoder. Right? You could also pass it to LLM encoder decoder model if that is what is preferred, and they basically pre-trained in both scenarios with just a decoder kind of a model, a frozen decoder, and also with a encoder decoder kind of a model. So remember again, I mean, the LLM decoder or the LLM encoder decoder are kept frozen, so they are not trained. They are basically just kept frozen. So if you really just look at this part, you should really think about it as if somebody gave you input image and input text, and you transformed it into a fixed size representation, soft representation that is not interpretable, but it's very, very awesome because your LLM decoder gives you really good outputs based on that. Okay, so it's probably more like a compressed representation where the LLM leads to super awesome generative outputs. Okay. So that's that. And again, I mean, to train such kind of things, you basically need a whole bunch of image caption data. And by this time, people had moved way beyond the typical small MS COCO data set and come up with interesting data sets like SBU as well, so as to train these kinds of models. Okay, that's BLIP and BLIP 2. People, I mean, before we come to larger models like GPT-4 and so on, people also tried other kinds of architectures. For example, another popular one was this mPLUG model, where the idea was to basically use, and there have been these instruction following multimodal models. mPLUG is one of them, but there is also LLaVa and GPT-4, MiniCPM-V, and I'll talk about mPLUG here, but we'll also talk about MiniCPM-V and LLaVa later, where yes, you do, I mean, it's also pre-trained on image text pairs and lots of pre-training data. Some of them basically have different designs for the visual linguistic encoder, but typically the decoder guy remains the same. Okay, so this is the mPLUG architecture where the decoder guy is exactly the same. No changes here on the decoder architecture. It basically just takes the shifted outputs as input text, has causal self-attention, cross-attention, and then feed forward. So nothing changes there. But on the encoder side, this one is a slightly different architecture. In Visual BERT, basically you had early concat. In VilBERT, basically you had layers. I mean, basically there were like 2 towers. There was a vision tower and a linguistic tower, and then in between you were basically doing some information propagation through the co-transformer layers in that senses, right? This one also is slightly similar to that, but then does slightly different work as well. So let's basically look at the architecture, right? So there's a visual encoder and there's a text encoder. Okay. So after a few layers of visual encoding and text encoding, you do compute your ITC, your image text contrastive loss. Okay, so that basically is going on as usual. You should really now think about this guy as a clip guy, right? Clip kind of pre-training, right? But then beyond that, what it does is to also apply the mask language modeling and the ITM losses. So rather than just depending on the three, ITM, ITC, and language decoding, it's also doing mask language modeling. Okay. Where mask language modeling is the standard mask language modeling. You take the input text and mask out a few tokens and try to predict those tokens. Okay. But what is going on here is that there is a visual tokens which are being passed to your transformer decoder layer transformer encoder layer as it is, right? But then the text tokens are being processed through this cross attention. Another kind of they call it asymmetric asymmetric co-attention kind of a layer. Okay, and this layer basically has a self-attention, has a feed-forward, but it also has a cross-attention, taking the influence from the vision stream in that senses. Okay, and then the idea is that you repeat this thing. Sometimes you have one transformer encoder layer, and then you basically repeat this thing like n times. Okay. So the architecture is overly complex if you really think about the simpler architectures that exist today. By the way, all of these architectures are great, but then today what exists is much more simpler architectures. But people did make those changes. And again, when it comes to these interesting changes, they are interesting from academic perspective. When you really think about deploying them at scale, it becomes really complex to deploy such architectures, because when you change these things, when you make these changes, literally you're making changes in the transformer. I don't know what do we call it. Maybe we should really call it the transformer encoder, because everything is encoder anyway. You're making those changes, but then your primitives are changing, which basically means your GPU kernels that you wrote for doing any kind of optimizations will have to be rewritten. Okay, so unless this gives you significant benefits over just using a standard transformer encoder, standard clip encoder, and decoder, people typically tend to not use them in industry. But that said, yes, I mean it's a great thing, because mPLUG paper, all of these papers obviously showed that their results are better than the previous ones. I excluded those because that's going to be very boring here, right? If you really wanted to look at the results, you can look at them in the paper also. Okay. So that was the mPLUG paper, and after that, models are super simple. So people came up with this LLaVa model, and the name itself should tell you it's basically processing visual plus llama. Okay, in that senses. And this model, as you can see, this is the architecture, and I mean maybe I don't even need to describe that architecture to you. It's like extremely simple. Okay, the idea is that. But powerful. That's the most important point. It's simple and powerful. Pluggable components, super simple to deploy. From deployment perspective, maintenance perspective, it just becomes so easy to work with these kinds of things. Okay. The language model here is an LLM, could be llama, could be anything else, right? Later, basically, people call it MiniCPM-V. They just use GPT-4 as the language model in that senses. Okay, but here in this LLaVa kind of a framework, they basically had llama as the language model. Vision encoder is basically your VIT kind of model. You take the vision encoder, you basically have a projection layer. So you take the vision encoder, you keep the vision encoder frozen. Okay, you don't change that. You take the language model, you keep the language model also frozen. Don't change that. Only change the projection layer. Only basically train the projection layer. That's it. Okay, you have a lot of image caption data. Sure, use that to only change the projection layer. You have a lot of visual question answering data. Yes, I mean you can use that also. So basically, take the visual question answering data, take the image, pass it to the vision encoder, take those text tokens, pass them as is directly. Text tokens, pass them as is in your language instruction, and let it generate the answer. So you can actually now train the model on all kinds of multimodal data, not just image captioning data. Okay, training is also easier because you see, if you are keeping components frozen, you don't really need too much of iterations to train these projection layers. Obviously, if you have more data, clearly it leads to better results. But the idea is training also becomes easier. Okay. They have some details also here. So for example, if you are training on conversational kind of data, so and they actually trained on conversational kind of data, for the first turn you could choose to keep the query first and then basically the visual part. So query is basically text query and then the vision part, right? Or you could keep the image first and then the text part. Okay, so basically you could keep the query first and then the image, or keep the image first and then the text. Okay. Now it has implications. So basically, for all the other remaining turns, essentially they are keeping the query first. Basically, sorry. Yeah, so for the remaining turns, obviously you just have the query. You don't, because there is they work with only conversations which have one image. Yeah, that's that, right? So whether you keep the query first or the text first has implications in the sense of KV caching. So remember, when you're doing conversations, if some part changes while some part is constant, you would want to keep the constant part first. Okay, so that you can do KV caching and essentially not really, as you get more and more things, you don't really essentially recompute the decoding part again and again, right? But anyway, in their case, basically randomly chose between both of them just to essentially ensure that the model basically can also deal with images that come after the first text turn rather than actually always considering the image first. Okay, so LLaVa, from an architecture perspective, it's super simple. Essentially, you have image, pass it through a frozen image encoder. You have text, pass it through a frozen LLM, but prepend it with the image tokens. That's basically that. Okay. Then people came up with Video-LLaMA. Now, Video-LLaMA has to take multiple multiple image tokens in that senses, because video is basically, after all, multiple frames. Video-LLaMA specifically not just focused on the visual aspect of videos, it also focused on the audio aspect. Okay, so if you look at the decoder, well, decoder is a frozen LLM. It could be LLaVa or Llama or Vicuna. Vicuna was also popular. I'm not sure if you folks know, but Vicuna was a small effort from Berkeley guys, which exploited the flourishing that happened in those days. So what happened in those days was Meta released Llama, which made academicians to essentially nicely train models, fine-tune models on their side. Microsoft released LoRa, which basically enabled faster fine-tuning. There were ChatGPT kind of models which enabled synthetic dataset generation, and all of those three combined, people came up with Vicuna, a very good recipe. Spending very little amount of research efforts or any engineering efforts, but coming up with a much better Llama model, which was called Vicuna, right? And the same thing happened with another story called Alpaca at Stanford. But anyway, so basically, sorry for the digression, but the point is that the LLM is basically the standard LLM, right? The idea is that since it's a Video-LLaMA, well, it has to sort of take video signals, visual signals and audio signals. So that's what this branch is doing. It's basically taking the video signals, visual signals, and this branch is basically doing the audio signal processing. Okay. So when you have a video, you basically break it down. You take the video and the audio out, and I'm sure everyone here has used FFmpeg to basically get the two tracks out anyway, right? So when you basically take the video signal, well, it has multiple frames, and if you have sampling at the same sampling rate, you would end up with different number of frames depending on the length of the video. Okay. So they take each of those frames, pass it through a VIT or some visual encoder, and then finally pass it through a Q former, because well, some videos maybe you are also doing some frames, you're also doing crops, which basically means that your VIT model can lead to different number of tokens per image. But ignoring that complexity, the idea is that you basically get same number of tokens per image. Okay, so same number of tokens per image. But then you can have different number of frames. So you have to basically also deal with different number of frames, which is why they basically use a video Q former. Now we know what Q former is. Q former is that guy which basically takes variable number of inputs, but then can finally lead to a fixed number of learnable queries. Okay, so that basically gives you a fixed size representation for the video. And the same thing you do on the audio side. On the audio side, obviously you need to use a specialized audio encoder. Particularly, they use the audio spectrogram transformer. So audio can be represented in the spectrogram space, in the frequency space. Some of you might have used Audacity or PyAudio to generate spectrograms, so audios can be also represented as images in that sense. The spectrogram is an image after all. Okay, then you have this audio spectrogram transformer, which is basically specialized, trained on audio-based data. This is the same spectrogram transformer which is also used as the encoder for image bind model, which we discussed yesterday. Okay, rather just talked about briefly yesterday. Right? So you take this audio transformer, audio encoder outputs, and again, you compute this thing for fixed size segments. So if your audio is very long, you would end up with lots of tokens. If your audio is small, you will end up with smaller number of tokens, and therefore you pass it through an audio Q former so as to finally end up with fixed number of tokens. Okay. And then you give it to Llama. And again, this fixed number of tokens was very, very important at that time. Again, 2 years back in time, because Llama also had like limited. The Llama 1 model had like 2K window. Okay, so essentially, if you had like you see, I mean, like 5 images, and each of those images basically, I mean, these images were like 1024. You had like 16 sized patch size. I mean, 1024 by 16 is what? I mean, I think some 56 maybe, or something around that, right? 50s, 1000, yeah, I mean, something like that. So I mean, yeah, a few tens, let's say, right? So basically, very easily, even with 5 images, you can actually fill that space of the limited token window very quickly. I mean, but obviously, you also have to process the audio modality. So the idea is that whatever be the size of your video and the audio, you wanted to compress it down to limited size so that you can fit all of this in limited budget and make it work. Okay. So that was Video-LLaMA, trained in different parts now. So obvious things are you train the video branch separately, you pre-train the audio branch separately, and then you essentially learn the nice projector layers. So the projector layers are trained at the end. Okay. So that's Video-LLaMA. MiniGPT-4, now as you can imagine, it's not a new thing anyway. So you take image, pass through the Q-former. LLM basically is Vicuna model or the more powerful GPT-4 model, and all they want to train is this linear layer. So as you can see, these two are frozen. Only the linear layer is what is trained. There are more details, and in the interest of time, I may not really talk about all of those details. But if you have more rich data, and you have richer LLMs, you automatically get the benefits of richer LLMs as they become better, because your model is your overall architecture just depends on those richer LLMs anyway. Right? And then people started using them. In fact, 2023, at the end of it, people realized that yes, text generation using multimodal inputs is a reality. And people started using them for various purposes. In fact, in Teams, Microsoft Teams, we started integrating this for speech to text. I mean, obviously, speech to text was way better even before these models, but it's also a multimodal thing in some ways. That quality became better, but it became even better with recorded videos. So Teams quality with recorded videos is super awesome. The transcript quality that you get at the end of it, right? So here is basically just a speech to text example, but then there is also a lecture video. So these models are the ones that helped basically generate very awesome awesome outputs, things that people have obviously not seen before. So for example, you could take a nice 45-minute video and create slides out of it. Those slides may or may not be really perfect, but hey, that is something for you to start with. So essentially, rather than starting from scratch, that's a pretty good. These are slides. This is basically taken from OpenAI's blog, GPT-4o model. GPT-4o was I believe GPT-4V was the first OpenAI multimodal model. GPT-4o is an improved version on that, and they basically showed yes, their model could actually do long video processing also, thanks to some of these architectural advancements, and generate awesome text. Okay. So there's a more recent MiniCPM model, but I think I'll skip that for the sake of time. One last thing that I want to touch upon before we sort of stop is this interesting piece of work which happens in the UX space, user interface space. Okay. Now we engineers typically feel, oh, user interface is for some design people, who cares, and so on, right? But the interesting thing here, how do you make these models multimodal understanding models? Also, in an agentic world, right? Also, basically do user interface tasks automatically, right? So, for example, if you think about flight booking, it's a very complicated task. I mean, if you think about or cab booking is an even more complicated task where randomly the cab gets cancelled, and or the guy doesn't want to cancel, and so on. So a very complicated task, right? As complicated as driving on Indian roads, right? So, but anyway, and here then the agent needs to be able to understand the UX controls which exist. It needs to understand you see the functionality that each tool provides. It needs to be able to also decompose large tasks. So now we are talking about an agent which is supported by all of the multimodal architectures that we have learned so far, right? So it should be able to decompose the task as well. So take the task of flight booking and figure out, oh, I have to basically first figure out in the user interface that is given to me, how do I basically find the set the origin city, then set the destination city, set the number of people who are traveling, set the dates, and then essentially check out what the results look like, because it's not like I will be shown the results always. Maybe internet connection breaks and I get a 404. Then what to do with it, right? So or I get like connection expired or whatever I get, right? How do I deal with it, right? So these are some of those snapshots that I'm showing here. It also needs to basically be able to understand, oh, one milestone is achieved. I've been able to set the origin city, and that's a milestone, right, in the entire planning, right, and so on. So sometimes it also needs to backtrack or reflect. I did something. I clicked on the search button, but here I'm not seeing any results. What happened, right? So essentially, is there something wrong? Maybe it needs to keep polling, keep waiting, or maybe the search results are still populating, right? So there's a huge lot of stuff that we humans do, which needs to be sort of mimicked. And interestingly, people have been training these kinds of models to be able to do these kinds of tasks. Again, I'll skip some slides, but it's very interesting when you read through them, what kind of stuff, what kind of reasoning that this model has to do in an agentic way to take the multimodal input and figure out the next step to be done. Okay. What is exciting to understand is how do people train these models. Now, UX controls are not simple. They are not like typical cat dog images. So you don't learn that by learning from ImageNet. You don't learn that stuff at all. It's a different domain altogether. Okay. So they did a whole bunch of interesting learning by taking a huge lot of user desktop snapshots that you see here. So I know this image is very, very busy, but you see this desktop picture, and they basically gathered a crazy amount of labeled data, question answering data. What does this particular icon at the left bottom, shaped in a particular form do? That kind of stuff. Okay, and element description also. So for everything that you see, and again, I mean, if you see the screen, right? I mean, there are probably like 100 elements that you see there, right? And we are like super awesome, geeky people. We understand the interface so well, right? Show it to my mom, right? I mean, and she's never going to use this, right? But anyway, right? So the point is that all of these things, and then talk about actions. This is just a static snapshot. What happens if you click here, or rather, if you basically were at this snapshot and then next, this is the snapshot. What action might have been taken to basically get there, right? So those are the tasks that they train for, and there's a very interesting field altogether by itself. There is active research work being done in this field, and I'll basically, again, due to time limits, I'll basically skip that. But there's active work which is being done in this field to extend this work now to mobile screens, because they are even more complicated. Desktop screens, sure, I mean, you have so many controls, but you can actually visualize them and hover over them to understand and so on. But mobile screens, well, I mean, it's super complicated because in the compact screen you have, and sometimes broken UX as well, you have like so many things. So people are actively working on mobile screens. There's no model for now which basically can do interesting multimodal processing over mobile screens and then do some automated tasks. In fact, and there are like, again, other stories as well. So at Microsoft, internally we developed a voice-based troubleshooter. Okay, I can't, install a printer. So let me just talk to my device. Hey, install the nearest printer. And I mean, it gets into autopilot mode. It basically just takes a snapshot of whatever is being visible on my screen, presses the Windows button automatically, and also talks while it's doing that. I mean, it's speech enabled as well. Speech to text, text to speech is good, right? And then it basically, figures out, oh, Windows button, it shows settings, click on settings. So it basically figures out where to click. Clicks on settings. Settings, okay, there's some printer option, printers and devices. Okay, click on that, and then, add a printer, and then all of that, right? But again, so all of that is supported by this UiTars kind of model, so that you know where to click and so on, right? But then, there are deployment challenges, there are privacy challenges, so that will not come into Windows ever, because it's just that there are privacy challenges. You can't capture user screen like this and so on. Maybe it will come up at some point with lots of permissions being asked from the naive users as well, that, hey, please understand we are taking snapshots of your screen and so on, right? So in short, in this session, well, we went over a whole bunch of models. Hopefully I motivated you, and well, you have been using these models for various use cases anyway, right, with many, many applications. But we also talked about several architectures like Frozen, Flamingo, and that's history. That's basically the way it evolved, basically, right? In Frozen, I mean, people did not even realize that you don't need to really retrain the entire vision encoder. You can basically just retrain projection layer. And then there were models which basically tried to mess around with the encoder and come up with better and better encoders, visual linguistic encoders in that sense, more or less keeping the generation part more or less just the standard transformer decoder, right? There are models which have basically, tried to include the visual and audio input as well. And then, specialized models basically which try to do generation and reasoning in user interface space, complex user interface screens, and so on. Okay. That's it for this session, folks. Hope you enjoyed the session. It was a quick glimpse into what is going on in the world where inputs are multimodal, but the outputs are text. Obviously, yet another interesting area is where the outputs are also multimodal. You have image generation and video generation and multimodal generation, but that's a story for some other session. Thanks so much for being a great audience, and the interesting questions, and we'll stop here. Thank you.